this computer. All right, so section 4.1 is on extreme values of functions. And really, chapter 4 in general, we are going to be focusing more on the actual applications of derivatives. The main application we really already started to look at was with min and max, so finding extreme values. So we've actually done a lot of the work to understand today's lesson. We're just going to make it formal and really kind of look at a few specific things that are interesting in terms of things that will always happen and in terms of making sure we have the terminology. All right, so we will now look at applications of derivatives, particularly in optimization. So our goal is to find extreme values. And again, what do I mean by extreme values? Things that are like maximums. So extreme values are maximums or minimums. So if you're reading through and view an example or something like that, you'll see this notation right here. Don't get too hung up on the notation, but what we're going to start to understand is the difference between an absolute maximum and a local maximum, and then also an absolute minimum and a local minimum. So an absolute maximum is going to be some value. So it's going to be a number, and let's just go ahead and visualize it down here below. So if we were to go ahead and just take, let's say, just a generic graph, and let's say we have some function that looks like this right here. Yeah, I don't like that one. Let's try it one more time. Okay, good enough. But let's say it starts here at A, and let's say it even goes down a little bit farther right here at B. So what we're going to be looking at are the maximum values and the minimum values, but let's go ahead and look at maybe right up here. This right here is a maximum value and is going to be, let's say this right here is C. So this would be f of C, this y value, so the y value would be f of C. And that right there is the actual absolute maximum. All right, and then what about right here? Well, if what we're going to start making the distinction of is between absolute and local. And again, that we may cover it a little bit more later in the lesson, but I think it's nice just to start out with looking at, okay, right there, that green dot, we have a maximum. Why do we have a maximum? Because if you look at what's around it, well, it's higher than what's around it. So we do still have a maximum, but this is referred to as a local maximum. And what's actually pretty interesting is we have more than one local maximum. For example, this right here is also considered a local maximum just from what I said. If you think about, is this point on the graph higher than what's around it? Yeah. So therefore, you could go ahead and consider that this is also a local maximum. So again, we used the word absolute. You'll also hear me sometimes say the word global extrema. So absolute, global, I think this book uses the word absolute. But now the question then I would also ask maybe before we move on to an example is where are the minimums? So if you think you know where the minimum is, go ahead and throw it in chat. Or you could log on or log on the audio and say, where would a minimum be?
Would the minimum, oh, just kidding.
Yeah, so the minimum is going to be the lowest point, and we want to be careful what we say by point. So if we're looking at it like, and Max, maybe were you looking at like maybe right here? Let me change colors. So you may have been looking like, oh, right here at this right here at B is the actual lowest point on the graph. So
Yeah.
remember, this would be f of B. So the actual absolute minimum, what would that be? That would be f of B. So it wouldn't be the whole point. It would just be f of B, whatever that value would be. If we had a function associated with it, we could go ahead and plug it in. So notice that that is an absolute minimum. And notice that this is also a local minimum. And the other thing to note is that it's at the endpoint. So notice here, this graph doesn't go on forever left and right. It just has this little piece right here between A and B. So then we want to think, what is the other minimum? There's another minimum somewhere here.
Between the two maxes.
Say again?
Between the two maxes.
So actually there's two more. Yeah, so there's one more right here. So you can see right here, this is another one. So this would be another, let's say this would be D. So f of D would be another minimum, and this one would be a local min. And then there's one more minimum. Does anyone see where it would be? Or what it would be, actually. We could even say what it is.
Okay.
And that's pretty close. That's where it's at. Now remember, the actual value at A is the minimum. So what would that be? It would be right here, which would be f of A. So that f of A is the actual local minimum here.
So you're not looking at like plotted points, you're looking at the points or the X and Y value.
You're looking specifically at the Y value.
The Y value, okay.
So you can see right here, if we look at what I said above, the absolute maximum value is the actual value. And that occurs at some point. So as we would say something like, let's look at this one right here. We would have a statement that's like, we have a local minimum of f of A at x equals A. So this is kind of the statement you'll see.
Okay.
So the thing to note is the actual value is what we're concerned about.
Okay.
So we're going to maybe take another 15, 20 minutes to explore this in a couple of different contexts. And what we're going to go ahead and now do on the next slide, or at the bottom of the page, I have this printed out in pages, is we're going to look at a given function, so namely the sine and cosine. But notice the sine and the cosine are restricted to certain domain. Before I go into the explanation, are there any other questions on this little image from above? Okay. The endpoints of A and B. Okay, yeah, I was just reading what you said, chat. Yeah, so the endpoints in this case are where where minimums occur, and then the Y values associated with
the value
are the actual mins.
Okay.
Great. So again, on the example down here below, we actually have the domain and range restricted. So the domain for the sine function is blue. We're looking at negative pi over 2 to pi over 2. And that's actually for both of them. We restricted it from negative pi over 2 to pi over 2. So if we're looking at the sine function, the one here in blue, think about what is the absolute maximum value. So if we were to go ahead and look at sine, what value would be the absolute max? Anyone think they know?
1.
Yeah, it would be up here at 1. And notice again, we would have a statement that's something like this. The value would be 1, and that occurs at x equals pi over 2.
Oh, yeah.
And you could even see, where did this 1 come from? This is sine of pi over 2. So that's what above we just said, like f of a, f of b. Well, more specifically now, it is the function evaluated at the x value, and that y value is the actual maximum. Now, in the case of the minimum, then you can see in the blue graph, the smallest value is the smallest y value is -1, and that's at x equals to negative pi over 2. So now we could look at the cosine function. And if before I spoil it, go ahead and just kind of take a moment, look at it, think if you could figure it out. So the absolute maximum value, does anyone think they know that one?
1.
It's indeed going to be 1. That's going to be at x equals what?
0.
At x equals 0. I like the interaction, so by all means, if you would like to turn on the mic, it kind of helps me know what to explain and what to explain. So the absolute minimum here, we have to be a little bit tricky, or we got to be a little bit careful with, because, well, let's think about y value. What is the lowest y value for cosine? Here and here is where we're looking as the slowest values. What y value is that there?
0.
This is 0. So the absolute minimum value is 0. And notice that that value can actually occur in more than one spot at x equals to plus or minus pi over 2. So the fact that they are exactly the same level means that, hey, the value is still 0, but it can occur at more than one spot. Are there any questions on the trigonometric examples down here below?
No.
Awesome. So now there's maybe something that's worthwhile pointing out. Notice on the example up here above and down here below, these are on a closed interval. So a closed interval just means that it's going to be restricted to some part of the domain. So like negative pi over 2 to pi over 2. In general, sine's domain or cosine's domain goes on forever. So there's something known as the extreme value theorem. And this is really kind of an interesting idea. And it's, again, there's a lot of terminology up above that we'll read through, but it really boils down to just 2 things. And I'll go ahead and highlight the important words and then summarize it over here. So if f is continuous, so we're looking at the functions that are continuous on a closed interval, and a closed interval is notated with closed brackets like that, then what we're guaranteed to have is an absolute maximum, and we'll use a capital M to represent that, and an absolute minimum, and we'll use a lowercase m to represent that. So if we have a function that is on a closed interval and is actually continuous, these 2 properties will guarantee the extreme values. Extreme values. And the thing that's worth noting is to make sure you also check those extreme values could be at the endpoints. So possibly at the endpoints. They don't necessarily have to be in the middle of the interval. So we have the 4 scenarios over here. In the general sense, you can see right here in the top left, A to B is closed. You have the maximum right here, the minimum right here. It may be that you have the maximum, in this case, the maximum is up at the top in the interior point where the minimum is at the end point. You may also have the reverse of that, where the minimum is in the interior and the maximum is at the end point. Or it could be the case that both your maximum and your minimum are at endpoints. So again, that's things we explored in the last few examples. But we'll go ahead and just look at the scenario where we drop those two scenarios, like the fact that we have to have a closed interval and a continuous function are what makes it so we're always guaranteed some optimization. So this will show up more when we do in 4.6 applied optimization. For example, like the construction of a box, like that has a closed interval. Like you have to have a box. You can't like go into non-existence or something like that. So a lot of real applications will have some natural closed intervals, so it's a problem that you can actually optimize. So down here below, we just look at a few scenarios where we maybe aren't continuous or where maybe we're not on a closed interval. So these first few blanks just reiterate what we said was important above. And then we'll also go ahead and look in response to a question in chat. Can corners and cusps still be extreme? Yes, they can, and we'll go ahead and see why that's the case here pretty soon and how that shows up and how we can find those. So yeah, corner and cusps still will actually be relevant for extreme values. So note that in order for the extreme value theorem to hold, the function must be continuous, and the interval must be closed. So again, closed means that it also is going to be finite. So like, even if you close like one side and the other side is, this is like half open, but we'll consider this one down here below as both directions go on to infinity. So if we look at this first example, we have a point of discontinuity here at x equals 1. So notice, well, what is the absolute minimum? What is the absolute minimum? Does anyone think they know?
0?
Yeah, it's 0. Because the smallest y value is right here. Well, what is the absolute maximum?
0.9.
And then you may be thinking, oh, is it 0.9? Well, you can get closer. You can go 0.99. You could get even closer and closer and closer, but you'll never actually be able to get to 1 because of the open dot. So notice is maybe you're like, oh, you're tempted to say, oh, it's 0.9. But the thing is, you can get closer and closer and closer. So, but you'll always be able to get a little bit closer. So this is the scenario where there is no absolute max. Thanks, Max. All right. So, and the reason we don't have an absolute max is because, of course, we have this point of discontinuity is continuous everywhere except at x equals 1. And down below, you can see right here, the domain for this function is -infinity to infinity. It's an open interval. It goes on forever in each direction. So in this case, there is no max or min, not local or more absolute. So the function does not have a max or min on its domain, which is -infinity to infinity. So there's no max or min. So what are the two conditions for the extreme value theorem? Continuous function, closed interval. If you have those two things, you are guaranteed an extreme value, an absolute extreme value that is both a minimum and a maximum. All right. So what we do want to start to do is bring the idea of derivatives back into play. But before, and this will go with a question that was asked in chat, can corners and cusps still be extrema? Well, let's go ahead and look at this one right here. And we've already talked about this a little bit in the context of the first slide. Before I go into that, let me just pause. I forgot. Does anyone have any questions off this page? Okay. So a local extrema, also sometimes referred to as relative extrema. So your aunts and uncles, relatives, not relevant at all. Just give them time to write. So you can see we talked about this a little bit on the first slide, just while we had the full context. But you can see right here, the endpoints right here is the absolute minimum. And the absolute maximum is right here at f of d. So this is f of d up here. That's the actual absolute maximum. And this is, it's a little hard to see, so let me zoom in a little bit more, but you can see this kind of goes up here. It has this nice curve to it, then it kind of comes like this. So this is a corner. So we do want to remember, do derivatives exist at corners? No, they don't. So we'll want to go ahead and consider that here in a few minutes. But notice again, the absolute minimum is over here at the endpoints. You could have more than one minimum. These are local. And the absolute minimum is still a local minimum. So before we go ahead and bring the derivative into play, let me just go ahead and give a moment for you to find those extrema. It sounds like a really lame game show. But notice how this is worded. At which x values does the function have extrema? Notice that we don't have the y values given to us, so we're just looking at where they occur. We're not actually looking at what they're at. Or I mean, we're not actually looking at what their values are. So let me go ahead and pause for maybe 1 to 2 minutes just to go ahead and give you an opportunity to think through this, ask any questions if you have any. And again, if you're watching to this recording later, I would encourage you to pause it or fast forward depending on your mood. Just don't mute it. I mean, that would be no fun. But go ahead and let me give you a moment to think through it. If there's a question, do feel free to ask. All right, let's go ahead and look at this together. So let's see the global maximums. For number 1, the global maximum is up here at B. It's at an endpoint. And if we were to look at the global or the absolute minimum, so again, remember this is global or absolute. Both words are used interchangeably. If we were looking at the global minimum, we would look at C2. Then we would have the max we would have a local maximum at C1, and we'd also have a local minimum at A. But I am not completely correct here. What have we missed? Anyone think they know? Feel free to log on to audio if you think you know.
Aren't the global ones also locals?
Exactly. So the local max at C1, what's the other answer that needs to be there?
B.
At B. And what about the minimum? There's a minimum at A, but where else?
C2.
C2. Very good. So make sure you realize that global or absolute also are local. And in the case of 4, notice that we don't have this continuous function, nor is it closed. Do we have any sort of global, extrema? Anything that's higher than everything else right around it? Good. No, we don't. Correct. So there are no maximums or minimums. So if we think about the local, though, we have to be extra careful. Do we have a local max? Well, a local max means it just needs to be higher than what's around it.
So would it be
Say again?
would it be A? Or
So
no?
notice the function's not defined that here at A. So f of A is undefined. The graph does not exist above A. So like if you were to draw a vertical line, there's no graph. So so the value has to, of course, be defined.
It'd both be C.
There would be a local maximum indeed at C. So let's think about C right here. So local max at C. And let me just go ahead and kind of look at how the wording is above, and I'll explain why that is a local max. So a local max is a value at some point C within its domain if f of x is less, so everywhere else on the graph is less than or equal to C for all x lying in some open interval about C. So think about this open interval about C. You could go ahead and just go ahead and look maybe from like a little bit left of C, a little bit right of C. And if you were to just trace this part of the graph right there and let this be the endpoint, is this value higher than all of these? Yeah, this one is a little bit higher. It's up here where all of these are down here. So that makes this, even though it's just an open, there's an open dot here and the function's combined up here, that is still actually a local maximum. So that is why we have a local maximum at C. Because I'm able to create some open interval, doesn't matter how large it is, just that everything else in that interval is smaller than that. And if you think about that, we can't do the same thing for C, because again, you maybe try like this interval. It's just, there's no interval that you could construct in the same way like we did that purple one. So this indeed does have a local max, no local min or no global or absolute min. Any questions on this slide? Is anyone 8 for 8? I'm guessing usually the local max is sometimes the tough one. So, all right. So now what we want to go ahead and do is bring ourselves back into Math 2144 calculus and actually use calculus to understand these. So maybe we don't have the graph, or maybe we just want to go ahead and get a more precise answer and we need to go ahead and use the function. So enter the calculus. It sounds like a bad prequel or something. All right, so let's see what we have. Well, we have a new bit of terminology we're about to introduce. So I think we introduce it here. Or do we we introduce on the next slide. But we've actually talked about this a little bit. We have the first derivative theorem for local extrema. So if a function has a local max or min value at an interior point C of its domain, so that is to say, like it actually exists, there's no open dot, and if f prime is defined, so there's no corner or cusp, then f prime of C is equal to 0. So remember that this right here is the slope of the tangent line. So what does a line that has a slope of 0 look like? It's horizontal. So this f prime of C equals 0 is saying when we make the tangent line at x equals C, it is going to be horizontal because it's going to be equal to 0. And what we're going to do here in a few minutes is we're going to essentially take the derivative, set it equal to 0, and then solve. But we want to go ahead and highlight a few other scenarios where the graph has an absolute or just an extreme value, and we'll have to figure out, use a little bit more guess and check to determine if it's absolute or not. So let's look at that same picture down here below. So you can see here's the absolute mins. We have some local mins here and here. We have the absolute max, and we have the local max. So recall that if a function's derivative at c is 0, then the slope of the blank line at c is 0, and we talked about that above. That's to say the slope of the tangent line at c is 0. So let's go ahead and consider, where are these extreme values occurring? We have 1, 2, 3, 4, 5 extreme values. What is happening? Well, in the first case, we talked about that already. They're going to be interior points where f prime of c is equal to 0. And actually, since c is used here, I'm going to just go ahead and say f prime of like some x is equal to 0. We've set the derivative equal to 0. So what x values satisfy this condition? Where are interior points where the derivative is equal to 0? Where do we have horizontal tangent lines?
Oh, don't remember.
That's okay. And if, I'll just give everyone a sec. If you think you know, you can type it in chat or log on to audio. Where do we have horizontal tangent lines?
At the local max and local min.
So right here and right here. And more specifically, notice that that's our horizontal tangent line. This is occurring at x equals c and x equals e. So we have the scenario where you could have an extreme value occurring at interior points where the derivative is equal to 0, where there's a horizontal tangent line. All right. Let's also think about what is happening here? What is the derivative? Well, it does not exist. Why doesn't it exist? Because there's a corner. We go up, then we kind of do a sharp turn like that. So it's, again, this is still an interior point. And what is happening with the derivative? Where f prime of x is simply undefined. Where are functions undefined? Typically like negatives under a square root, or denominators in a fraction, or negatives inside a logarithmic function. So there's a lot of scenarios where the derivative may be undefined. So there's only one scenario in the graph above where the derivative is undefined. Where would that be? Right there at D. So x equals D is where we have the derivative is undefined. And then, of course, the third scenario. Where else can you have an extreme value? Well, we haven't talked about A or we haven't talked about B. Well, what is that in the context of this graph? These are the endpoints. So the endpoints are, in this case, x equals A and B. So these are the three scenarios we have to look at when we're looking for extreme values. These first two are related to the derivative. This one right here, you'll either be given, or if you're looking at a function that has a domain of negative infinity to infinity, you just ignore. So these first two are special, the ones I have a bracket. These are referred to, and this is critical, they're referred to as critical points. See what I did there? Okay. Any questions on anything from this portion of the notes? All right. So let's go ahead and look at the these critical points a little bit more closely and give a real function and a real computation to them. So there's my joke one more time. Still not funny, I get it. This is critical. The interior points, so notice again, we're just looking at interior points of the domain where the derivative is 0 or undefined. So we have two examples right here. It is important to note that it is possible for a point to be a critical point and still not be an extreme value. Just because it's a critical point does not mean it's an extreme value. It's just a scenario where there could be an extreme value, and we'll see that in below. So over here, we have a cubic function, and let's go ahead and find the critical points of x cubed. Well, what we're going to do is take the derivative. Y prime equal to 3x squared. And in order to find the critical points, what we're going to do is solve y prime equal to 0. So 3x squared equal to 0. Divide both sides by 3. Take the square root. So I'll show that. Divide both sides by 3. Then take the square root. You get x is equal to 0. This right here is a critical point. So there's only one, or CP for short. So let's look at this right here. The derivative indeed is equal to 0 because we have a horizontal tangent line. But do we have an extreme value there? No. Because see, if we look to the left, it's lower. If we look to the right, it's higher. So we found a critical point. In this case, the critical point is not an extreme value. Now let's look at this one over here, which is this radical function. So this could be rewritten as the cubed root of x. I take the derivative. I get 1/3. And then we have, I'll read x to the minus 2/3, which I'll rewrite as 1/3. And then in the denominator, I'll just leave it as x to the 1/3, 2/3, excuse me. So that's our derivative. Now, what if we set this equal to 0? What if you try to solve 1/3 x to the 2/3 equal to 0? Well, it has no solution. If you try to multiply both sides by 3x to the 2/3, your x will cancel out and you'll get like 1 equals 0, so there's no solution. But remember the other scenario where you could have a critical point. You could have a critical point also where the derivative is undefined. So CPs occur also when f prime is undefined. If you look at this, what value of x are you not allowed to plug in? Does this function have a denominator? Yeah. So what are you not allowed to plug into the denominator?
0.
0. And again, you could also solve do this by just looking at x to the 3x to the 2/3 equals 0. That implies that x is equal to 0. So these right here, we have critical points. Our critical points in both cases are x equals 0. And in these cases, they're not extreme values, but what we're going to learn, I think, in section 4-4, these are actually points of inflection. Inflection, yeah. And again, if you watched the video I posted a little bit earlier, right before we transitioned to remote learning, we talked about points of inflection as essentially when the growth rate of a pandemic or of the disease essentially starts to decrease and not increase as much each day, would be the point of inflection for that model. So the important thing is to note that things happen at critical points, but sometimes nothing happens in terms of extreme values. So let's go ahead and look at a couple examples of tying this all together where we do essentially the whole process. And of course, the homework may have a few harder problems, and I'll post to the work for the rest of them. But let's do example 2, and then let's also go ahead and look at example 2, and then this one down here at the end. So stuff happens at critical points. Any questions so far? I know this is right where it gets really tiring. 40 minutes of math, I'm getting a little tired too. But let us power through and finish up these last two examples. So find the absolute maximum and minimum of f of x equals x squared on this interval. So do we have a continuous function on a closed interval? This is continuous, this is a closed interval, so we're guaranteed answers. So what we're going to want to do is evaluate f at all critical points and endpoints. So let's find the critical points first. So let's find the critical points. How do I do that? Step one is calculus. Take the derivative. So we'd have f prime of x equal to 2x. Now what we'll need to do is take that, set that equal to 0, solve. You get x equals 0. This right here, my critical point is x equals 0. That was part one. Well, almost. That was part of part one. Evaluate f at all critical points and endpoints. Okay. So the other part to part one is to evaluate it at the endpoints. So f of -2, f of 0. So this is an endpoint. This is a critical point. And f of 1 is the other endpoint. So what is f of -2? You plug this in, you get -2 squared, you get 4. You plug this 0 in, 0 squared is 0, and plug in 1, you get 1. So what we learned from the extreme value theorem earlier is that a continuous function on a closed interval will have an absolute max and min. So step 2 is the answer to the question. The largest value is the absolute max. The smallest value is the absolute min. So the largest value in this case is 4. So the absolute maximum value of 4, where does that occur? At x equals -2. Where is the absolute minimum? What is the smallest value of these three? 0. And where does that occur? At 0. So we have 0 at x equals 0. So notice again, if we had the graph, and maybe you just thought about it before we got into this, but I'm trying to just show the calculus side of it. The graph of the function, wow, that was atrocious. Let's try that again. No, let's do that. Perfect. So it'll look something like this, and then something like this, where you have closed, closed, and then you can still see we have the absolute minimum of 0 right there, and then we have the absolute max right there. So that would be up here at 4. This would be up down here at 1. Not perfectly to scale, but that is how we use critical points to find extreme values. All right. So any questions on number 2? So of course, on number 2, we were restricted just to this closed interval. And let's go ahead and just look at this one a few pages over, where we're not necessarily concerned about the maximums. We just want to find the critical points. Well, let me, maybe again, one takeaway: to find the critical points, what do you have to do first? And hopefully you're mentally thinking, and does anyone know?
Take the derivative.
Yes. Find the critical points. What you're going to first do, step 1, take the derivative. Step 2, solve
For 0.
f prime of x equals 0. So you're going to set it equal to 0, solve for x. All right. So f prime of x, we're going to need the product rule here and the chain rule. So it would be first times the derivative of the second. The second is a chain rule, so it's 3 times 4 minus x squared times the derivative of the inside. plus the second, so 4 minus x to the third, times the derivative of the first. Any questions on the derivative? Looks pretty nasty, but let's go ahead and clean it up. So first times the derivative of the second. Yep. So then you would just have 3x times 4 minus x squared. This would be negative plus 4 minus x to the third. And I believe one of your peers actually encountered a problem like this earlier in the semester. Here is a trick. And then that's where we'll call it a day. And then I'll kind of leave you to finish off the algebra. Notice between these two terms, is there a something common between those?
4 minus x squared.
4 minus x squared. So what you could go ahead and do, factor 4 minus x squared out. Notice when you factor it out, you'll be left with just this minus 3x. And then you would cancel 2 of those out, and you would be 4 minus x. That's all that's left here, because the other 2 got factored out. Clean that up. You have 4 minus x squared, and then you would have minus, let's see, that would be minus 4x plus 4. And that is much easier to solve for x. And when you set each part equal to 0, 4 minus x squared equals 0 gives you x is equal to 4. And minus 4x plus 4, set that equal to 0, you get x is equal to what? 1. So what are your critical points? 4 and 1. All right. And of course, there's a few other examples. We may do these tomorrow, but before I end the recording, are there any questions relevant to this example?
How would we like enter this? Like, what kind of notation would we write the 4 and the 1 in?
I think it varies from on MyMathLab. You may just have to enter, like it may say, what are the critical points? It would just,
like 4, 1 or?
4, 1.
Mm-hmm.
So that's actually a great question. The interior point of the domain, interior point of the domain of the function where f prime of x is 0. So this is a little bit weird how this is worded. Great question, Alicia. See how it says the interior point of the domain of the function is where f prime is 0. So the actual point on the graph would be like 0, 0. But typically when we're talking about critical points, we just are going to go ahead and plug in. We're just going to be looking at the x value.
Yeah.
So make sure you just read that little text that says if it wants the actual point. But that's a good question. I'm going to have to look into that just to make sure.
Okay.
Because the way this is worded, it's just saying it just wants the x value, like it's actual a single point in the domain. It doesn't want the point on the graph.
Gotcha. Okay.
So, yeah, it's like the point of the domain, and the domain is just the x value. So I'm pretty sure it just wants the x value. Which
Okay.
is kind of misleading because a point's usually talking about a graph. But
Yeah.
this is worded in the context of the domain. So just
Okay, cool.
great question. And I'll look into that. So let me end the recording here just so it doesn't super long. And